Hi, I'm Albert, and I'm a PhD student at Eindhoven University of Technology in the Netherlands. And I am going to talk about the asymptotic convergence of dropout for shallow linear neural networks. This is a joint work with Jaron Sanders. So first, I'm going to talk about what dropout is. This is a regularization technique used in neural networks. And then I'm going to talk about the results of the paper. Finally, I'm going to give you a take-home message so that you can remember the main points. So Dropout first appeared and became famous when it was used in the ImageNet competition of 2012 by Krzyzewski et al. And they used this for image classification. And the idea was that they had a deep neural network and with many layers, convolutional and dense. And in the dense layers, they, while training, they dropped weights by setting them to 0 and training the network with those weights set to 0. And they did this on every step with different weights. And turns out that if you compare this, the training error for using this method, which they call dropout, and without, you see that the training set, the error is worse, while in the test set, the network generalizes better. So that means that it predicts better the unseen data points. So what actually dropout does? So we have here an example. So here we have some data points, X and Y, some space, and we have some risk. In this case, it's L2 risk. And we have the weights W2 and W1, which are matrices and represent the weights of the network. And here, for example, the weights are represented by edges here and nodes by these circles. The Q is a nonlinear function, and we have here the L2 loss. Usually, what you want is to find the good weights by using a stochastic descent or gradient descent of one of these variables. And what dropout does is at time t+1, you choose by randomly points nodes, and you by probability 1 minus p, you drop nodes with by setting the weights to 0. And once you have this subnetwork, you use this to compute the gradient and update the weights. Mathematically, this means that we use some filters, in this case, for these Bernoulli random variables with probability p, that multiply the weights, and we do this at time t+1. And so at time t+2, then we use the same with different filters, which we assume are independent from the previous ones. And then we do this until convergence. And of course, since we drop nodes, we can also drop edges or other sets. And so what is known about dropout? So dropout is widely used, even though it's not fully understood theoretically. In particular, P is usually chosen heuristically. And there's not a good choice for P given the data. And through the years, there have appeared many variants of dropout, like dropping edges, as I mentioned before, set of edges, or using different filters instead of Bernoulli, like, for example, Gaussians. And most work on dropout focuses on regularization properties, and I mentioned here some of them. But in this paper, we focus on something different. We understand dropout as a stochastic algorithm. And we look at convergence guarantees and convergence rates. And since we use the extra filters that are not present in stochastic descent, this should be a bit harder than vanilla SGD. So in this direction, we can mention two papers. One is a previous paper of my own, where we prove convergence. We have guarantees for dropout like algorithms, and in a toy model, which is aligned with depth L, we prove that in this model, the rate increases exponentially in the probability, where L is here the depth of the neural network. And in another paper by me and Generora, we prove the convergence rate for dropout in over-parameterized shallow neural networks, where the rate is 1 over t, where t is the horizon of the stochastic gradient descent, but this rate turns out to be independent of t. So what we see here is that we would like to see how this rate depends on the probability p and how it relates to the width of your neural network. So can we find this in some other parametric regime? And the answer is yes, and we do this for the shallow linear case in our paper. So now I'm going to talk about the model for the shallow neural network. The idea is that you have here some data points, X and Y, which we understand as matrices. And from these matrices, since it is by linearity, we can transform the loss function into a problem related to matrix factorization, where Y here it represents is given there is a transformation of the data. And here W2 and W1 belong to these spaces, and F particular is the width of your network. So if you now add moreover dropout, you can prove that what you're actually minimizing by doing dropout is this function J of W, which is the expectation over the loss function, where you also apply your filters. And in this case, if you compute this explicitly, you obtain something that has this term, which looks like the previous function, plus this regularization term, which makes a problem, add some regularization to the weights. And A and B depend on your filter distribution, which, for example, can be dropping nodes or dropping edges independently. That can be tuned depending on your distributions. And we have to notice here that this term is non-convex and is not a norm. So what you could use for this term alone may not work if you add the regularization term. So in order to prove now convergence to this loss function, we will look at the ODE method. The ODE method assumes that if you scale the step size appropriately, and you look at the stochastic process given by the iterates, then this stochastic process will converge its trajectory to a solution of the gradient flow of an ODE. And the ODE will be given by this one, where J is the loss function of dropout. And now the question is, well, can we give a convergence rate for this ODE? And that is our first result. So if Y is this matrix depending on the data, and sigma are the singular values, then denote M to be the set of minima of J, which is the loss function of dropout, and D to be the distance from a point to a set. And with this notation, we prove that when W is in M, for almost every W, generic is here. You can understand generic here as almost everywhere. If you don't know what generic is, then in a neighborhood of a point of M, then if you start initialize there, your gradient flow, you will actually converge to the set of minimizers. And this is and you converge exponentially fast. In particular, here we have some omega depending on your neighborhood. So how do you, but this is not enough, right? This is a guarantee, but we want to find a convergence rate. So we can actually compute the convergence rate in a subset of the minimizers. In particular, we assume that the minimizer satisfies this algebraic condition, which we can prove also that there will be always minimizers that satisfy this. And we have here a bunch of constants we can compute explicitly. But the important thing is that they depend on your parameters of the distribution, which are B and A from before, and F, the width of your neural network. And with these parameters, you can prove that whenever W is in this set, MB, then under the same assumptions of before, as you get closer and closer to this neighborhood, if you initialize there, you will actually converge to the minima, and the convergence rate will be close to this bound, omega W here. And this bound, if you look at this, has two terms. The first term is a global term that is depending only on MB, and the second term is a local term that depends on the point you will converge to. And here it is nice to see that this will also depend on your singular values and the dimension of the width of the neural network. So what can we say more explicit about this convergence? What are the consequences? So if the output dimension is, for example, 1, we can give an explicit rate here for dropout, where lambda here will depend on P in this way, and the rate that you obtain is this one. So here you see that you have P multiplying numerator, and you have the width of the neural network in the denominator. The consequence is now that you can optimize this rate by minimizing over P, and you will see that there's an optimal P which scales as 1 over square root of f. However, in most of the cases in practice, you are in an over-parameterized regime where f is very large, so the width of the network is very large. But what we see in those cases is that this term will not change significantly unless p is very small. So this turns out to be similar to the ReLU case in the Mianji and Arora paper, but is, however, not directly comparable since we have a similar result can be obtained for when dropping edges, where you only have to change the parameters a and b, and you obtain here the rate on that case. And just to give a brief proof idea, so the idea is for the proof is that we can adapt convergence result for non-convex functions by Feldman, Getz, and Jensen to the loss function of dropout. And I won't go into details, but the idea is that you try to lower bound in the directions orthogonal to M, and for that you use group actions. So if you're interested, you are welcome to look into the paper for more details. But this, after all, is a lower bound, because indeed the theorem just talks about a lower bound. So how sharp is this lower bound actually? So for that, we go over to numerics. And in order to see this dependence, what we do is we run gradient descent with fixed step size on the loss function dropout, and we feed the decay of your gradient descent for different properties p and widths and initializations to an exponential function. So here beta will be the convergence rate, estimate for the convergence rate. And since we have found a theoretical bound for this convergence rate, here we have a model where we have a parameter alpha, where alpha should be close to 1 if the model is correct, if our model that we have obtained before, the bound that we have obtained before is correct. So in this experiment, if we do this, and we do this for 3 different data sets, so for the first data set has output dimension 1. So this is for the superconducting temperature data set. Second one is MNIST with output dimension 10, and CFR 100 with output dimension 100. What you see here in the x-axis is how close is the U start unixized to the manifold of minima, and here in the y-axis you have alpha. And what you see here is that for the first data set and the CFR data set, you are very close, while for the MNIST you have some variance. And the reason for this is that these different points here represent how large how large of a set you use to bound to obtain the fit for your exponential function. And here we see that as we go to further away to close to convergence, this tends to 1. So this shows that, or at least it suggests that this is due to variance, not because it is significantly different from the other cases. And also mention that by estimating beta depending on f and p, we see in a different plots, which are not shown here, that you have a decay in f, which suggests that close to the minima, what you actually see is that the landscape becomes flatter and flatter, and you actually take more time to converge. So finally, I will give you a take-home message. So the first one is that the convergence rate for dropout depends intricately on the data, the probability p, and the risk that we have used. And since we have seen this for the linear case very explicitly, we expect this to be true also for the nonlinear case. And that would be interesting to see future work if that is the case also. We can have also seen that the dropout probability becomes less relevant when you are in the overparameterized regime in shallow networks, and which are actually what people use in practice. So this may be interesting for practitioners also. And finally, we have seen by numerics and the convergence rate that the numerics and the convergence rate suggest that the landscape close to minima becomes flatter when f so the width of the networks increases. So Those are the main takeaways, and you're welcome to look in the paper for further information, and you can ask questions if you are interested. Thank you very much for your time, and see you.